Tonight, we're going to answer a question most people have never actually worked through. How much of the universe could a single human life realistically cover? Not in theory, with unlimited time and unlimited technology, but with the years an actual person gets, the speed limit the universe enforces, and the propulsion humanity actually has. Every mile beyond Earth costs something: fuel, years, radiation, risk, and those costs stack up fast the farther you go. And the gap between what we imagine and what's actually possible turns out to be enormous. By the end of tonight, you're going to see exactly how far a human being can physically go, why those limits exist, and what it means that we understand so much about a universe we can never fully explore. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let's start with the boundaries of the problem. A human life, even a long and healthy one, gives you somewhere around 80 to 90 years. Subtract childhood. Subtract old age. Subtract the years you'd need to train, to travel, to actually do anything productive once you arrive somewhere. Astronaut candidates typically spend years in training before they're ever assigned to a single mission. They learn spacecraft systems, emergency procedures, and foreign languages for international partnerships, and, depending on the mission, entirely new scientific disciplines relevant to whatever they'll be studying once they arrive. Add that training window onto the front of any mission timeline, and the years available for the mission itself shrink even further. What you're left with is a working window of maybe 50 active years. 50 years to leave Earth, travel somewhere meaningful, and still have time left to call it an exploration. Not a one-way disappearance into the dark. That's the clock we're working with. So, here's how we'll map it out, piece by piece, starting close to home and working outward until we hit the wall that nothing gets past. Begin with the easiest target there is: the Moon. It sits 238,000 miles away on average, and Apollo astronauts covered that distance in about 3 days using 1960s chemical rockets. In the scope of a human lifetime, the Moon isn't a challenge anymore. It's a weekend trip, relatively speaking. 12 people have already walked on its surface. If space programs continue at their current pace, dozens more will follow within the next few decades. The Moon sits comfortably inside anyone's reachable universe, about as unremarkable a stop as interplanetary travel gets. Neil Armstrong and Buzz Aldrin spent less than a day on the surface during Apollo 11 in 1969. Later missions, Apollo 15, 16, and 17, stretched surface stays to almost 3 days. Astronauts had time to drive lunar rovers, collect hundreds of pounds of rock samples, and set up scientific instruments. Some of those instruments, in fact, are still transmitting data decades later. Total time away from Earth for an Apollo mission launched to splashdown was typically about 8 to 12 days. That's not exploration measured in years. That's exploration measured in a long vacation. It's precisely why the Moon remains humanity's most repeatable, most survivable, least biologically punishing destination beyond Earth. Space agencies are already planning to return, with programs aiming to establish a semi-permanent human presence on the lunar surface within the next decade. That includes habitats near the South Pole, where water ice has been detected inside permanently shadowed craters. That ice matters enormously, since future lunar explorers might not need to bring every drop of water with them. They could potentially extract it, split it into hydrogen and oxygen, and use it for drinking, breathing, and even rocket fuel. If that works, the moon stops being a one-time destination and becomes a genuine outpost. It becomes a place people live and work for months at a time, well within the bounds of a single human life. And it requires none of the propulsion breakthroughs the rest of the solar system demands. Current plans call for a small space station orbiting the moon rather than sitting on its surface, serving as a waypoint between Earth and future surface missions. Alongside it comes a series of increasingly ambitious landings intended to eventually place the first woman and the next man on the lunar surface. That would be more than half a century after the last Apollo astronaut left footprints there in 1972. Unlike Apollo, which was fundamentally a race against a rival superpower, these newer missions are explicitly framed around building lasting infrastructure. It's the kind of repeated, sustained presence that could eventually make the moon feel less like a distant, occasional destination, and more like a genuine extension of where humans regularly live and work, which is exactly why it's a useful starting point. It tells us that within our own solar system, distance measured in days or weeks is completely survivable. The real test begins once you start measuring in months. Mars is the next logical stop, and it's where the numbers start to get uncomfortable. Depending on where Earth and Mars are in their orbits, the distance between them ranges from about 34 million miles at closest approach to over 250 million miles when they're on opposite sides of the Sun. With current propulsion, a one-way trip takes somewhere between 6 and 9 months. Add time on the surface, waiting for the planets to realign. For a return trip, and you're looking at a total mission length of 2 to 3 years. That's still well within a human lifetime. Uncomfortable, dangerous, expensive, but survivable. Mars sits inside the reachable universe too, likely the first place beyond the moon where humans actually set foot. But there's a detail about Mars that most people overlook, and it matters enormously for our lifetime calculation. You can't just launch whenever you want, since Earth and Mars only align favorably for an efficient transfer roughly once every 26 months. That's when the two planets are positioned correctly for what's called a Hohmann transfer orbit, the most fuel-efficient path between them. Miss that window, and you either burn enormously more fuel to compensate, or you wait another 2 years for the next one. This means a realistic Mars mission isn't just a 6 to 9 month flight. It's a 6 to 9 month flight out, a wait of roughly 18 months on the surface for the planets to realign, and then another 6 to 9 month flight home. Total mission length, door to door, is close to 2.5 to 3 years. For an astronaut in their 30s, that's a meaningful fraction of their remaining working life. It's spent almost entirely off Earth, exposed to radiation, reduced gravity, and total isolation from everyone they've ever known, aside from their crewmates. And that's assuming everything goes right. No emergency forces, an early return, and the return vehicle, fuel, and life support all function perfectly for the full duration. Some proposals go even further and suggest the first Martian settlers might not plan to return at all. Given the sheer difficulty and cost of a round trip, they'd choose instead to build a permanent colony rather than treat Mars as a place you visit and leave. Whether that ever happens or not, it tells you something important about the nature of exploring even our closest planetary neighbor. It isn't a quick errand. It's closer to relocating your entire life for the better part of a decade, all to reach a planet that, cosmically speaking, is practically next door. There's a deeper motivation behind Mars settlement plans specifically, one that goes beyond simple curiosity or the thrill of a new frontier. Earth, for all its abundance, is a single planet, vulnerable to a long list of catastrophic risks. A large enough asteroid impact, a supervolcano, a pandemic, or any number of other events. However unlikely in any given year, these become statistically more probable the longer humanity exists as a species confined to one world. Some scientists and engineers have argued that establishing even a small, self-sufficient settlement on Mars would give humanity a genuine backup, a second location where the species could continue, even if something catastrophic happened to Earth itself. Critics of this reasoning point out that Mars remains far more hostile to human life than almost anywhere on Earth, even after a serious disaster. Its thin, toxic atmosphere, lack of a global magnetic field, and brutal radiation environment make the backup planet argument more symbolic ambition than practical insurance policy, at least for the foreseeable future. Both sides of that argument agree on one thing, though: reaching Mars, however difficult, remains the most achievable large-scale step humanity could take beyond Earth, within a time frame that current and near-future generations might actually witness. Beyond Mars, though, the picture changes fast. The asteroid belt sits between Mars and Jupiter, a scattered ring of rocky debris left over from the early solar system, and it's not the dense minefield you see in movies. Most asteroids in the belt are hundreds of thousands of miles apart from their nearest neighbors, and a spacecraft could cross it without ever coming close to a collision. The distance from Earth to the main belt ranges from about 200 million to 350 million miles, depending on which part of the belt you're aiming for. With current propulsion, reaching the belt takes a couple of years. Missions like Dawn have already done it, orbiting the dwarf planet Ceres and the asteroid Vesta, though those were robotic missions rather than crewed ones. For a human crew, a round trip to the asteroid belt would likely take somewhere between 3 and 5 years, factoring in travel time, operations at the target, and the return journey. Still within a working lifetime. Still, technically, reachable. But you're starting to eat into a significant chunk of those 50 active years just to visit one stop. The belt itself contains an enormous variety of destinations, not just featureless rubble. Ceres, the largest object in the belt, is actually classified as a dwarf planet, roughly 590 miles across. It appears to hold significant amounts of water ice beneath its surface, along with bright salt deposits that puzzled scientists when Dawn first photographed them. Vesta, the second largest, is a dry, differentiated body with a structure closer to a small rocky planet than a typical asteroid, complete with a massive impact crater near its south pole that exposed material from deep within its interior. Studying that crater gave scientists a rare, direct look at layers of material that would otherwise be buried far beneath the surface of any rocky planet. It's a kind of natural cross-section, carved out by an ancient impact violent enough to nearly shatter the entire body. Beyond the scientific interest, the belt has also drawn attention for a far more practical reason: resources. Many asteroids are rich in metals, including iron, nickel, and platinum group metals, in concentrations far higher than anything typically found in Earth's crust. Some also contain enough water ice to theoretically support fuel production or life support for future missions traveling even farther out. Whether asteroid mining ever becomes economically viable is still an open question, but the belt could someday serve as a waypoint, a place to refuel and resupply before pushing on toward the outer solar system. That adds a practical dimension to what would otherwise be a purely scientific detour. For now, though, a crewed mission to the belt remains a multi-year undertaking, a serious commitment of a life's limited working years, just to reach the first true frontier beyond the inner planets. Not every mission involving asteroids requires a multi-year journey to the main belt, though some of the most important asteroid-related work happens much closer to home. In 2022, NASA deliberately crashed a spacecraft called DART into a small asteroid moonlet named Dimorphos, successfully altering its orbit around its larger companion asteroid. That proved, for the first time, that humanity actually has a working method for deflecting a potentially hazardous asteroid should one ever be found on a collision course with Earth. That mission took only about 10 months from launch to impact, since Dimorphos orbits much closer to Earth than the main belt. It's a reminder that not every meaningful step in exploring and understanding these rocky bodies requires a decade-long round trip. Some of the most consequential missions are the ones closest to home. Now, we reach the gas giants, and this is where the timeline starts to feel less like a mission and more like a sacrifice. Jupiter sits about 484 million miles from the Sun on average, and depending on planetary alignment, the distance from Earth ranges from around 365 million miles to more than 600 million. The Galileo probe took about 6 years to reach Jupiter. The New Horizons spacecraft, using a gravity assist from Jupiter itself, made the trip in just over a year. But that was an unmanned probe, optimized purely for speed, not for carrying a human crew with all the life support, radiation shielding, and consumables that requires. A realistic crewed mission to Jupiter, accounting for the mass of everything needed to keep people alive, would likely take somewhere between 2 and 4 years one way. And Jupiter itself is only the beginning of what's there to explore once you arrive. The planet has more than 90 known moons, but 4 of them, discovered by Galileo Galilei back in 1610, dominate the system. And each represents an entire world worth exploring on their own. Io is the most volcanically active body in the entire solar system. Its surface, constantly resurfaced by hundreds of active volcanoes, driven by the immense tidal forces Jupiter exerts on it. Europa, slightly smaller than Earth's moon, is covered in a shell of ice that likely conceals a global ocean of liquid water underneath. Some scientists believe that ocean could contain more than twice the volume of water found in all of Earth's oceans combined, and possibly the conditions necessary for life. Ganymede, the largest moon in the solar system, is larger even than the planet Mercury, and it has its own internal magnetic field, the only moon known to generate one. That discovery surprised scientists when it was first confirmed, since generating a magnetic field typically requires a molten, churning core, the kind of internal heat usually associated with full-size planets rather than moons. Callisto, heavily cratered and ancient, may also hide a subsurface ocean beneath its battered, unchanged surface. Exploring even one of these moons properly, landing, studying the ice, searching for signs of biology beneath it, would likely require its own dedicated multi-year mission that's layered on top of the years already spent just getting to the Jupiter system in the first place. There's an additional hazard specific to Jupiter that makes exploring its moons even more difficult than the distance alone would suggest. Jupiter's enormous magnetic field, by far the strongest of any planet in our solar system, traps charged particles into intense radiation belts that surround the planet. Europa, in particular, orbits directly within one of the most hazardous regions of that belt. It receives radiation doses that would be lethal to an unshielded human within a matter of hours, and that even heavily shielded electronics struggle to survive for extended periods. Any mission planning to land humans on Europa's surface would need shielding thick enough and stays short enough to manage that exposure carefully. That's another layer of difficulty, stacked on top of the years already required simply to reach the Jupiter system in the first place. Saturn is roughly twice as far as Jupiter, sitting about 886 million miles from the Sun. The Cassini spacecraft took nearly 7 years to get there. A crewed mission would likely take somewhere in that same range, maybe a bit less with more advanced propulsion, but still measured in years, not months. Saturn's rings alone would justify the journey. It's a disk of ice and rock particles ranging from grains of dust to chunks the size of houses, a system wide enough to nearly fit the distance between Earth and the Moon inside its span. Yet, it's so thin that, proportionally, it's thinner than a sheet of paper laid across a football field. Scientists still debate exactly how the rings formed. They could be the shattered remains of an ancient moon torn apart by Saturn's gravity, or leftover material that never quite managed to coalesce into a moon in the first place. A close, extended human study of the ring particles themselves could likely help settle that question in a way that distant observation never fully can. But the moons are just as compelling as the rings. Titan, Saturn's largest moon, is the only moon in the solar system with a substantial atmosphere, thicker than Earth's, and the only other place we know of with stable liquid on its surface, in the form of lakes and rivers of liquid methane and ethane, rather than water. That thick, hazy atmosphere is part of what makes Titan such an appealing long-term research target. It offers meaningful protection from radiation that worlds like Europa simply don't have, potentially making extended surface stays. They're far more survivable for a human crew than almost anywhere else beyond Mars. Enceladus, much smaller, has geysers of water ice erupting from cracks near its south pole, jetting material out into space from a subsurface ocean. Cassini flew directly through that spray, tasting it with its instruments, and found organic molecules and hints of hydrothermal activity on the ocean floor below. Both of these small, icy moons rank among the most promising places in the entire solar system to search for life beyond Earth, and both would require dedicated landers, submersibles, or drilling equipment to properly investigate. That adds years onto an already years-long journey, just to reach the Saturn system in the first place. Imagine what actually standing on one of these worlds would be like, since the numbers alone don't capture it. On Titan, the gravity is only about 1/7 of Earth's, weaker even than the Moon's. But the atmosphere is so thick that the air pressure at the surface is actually higher than Earth's at sea level. That means a person could theoretically strap on wings and, with a bit of effort, fly under their own muscle power through Titan's hazy, orange-tinted sky. The temperature there, though, sits around -290 degrees Fahrenheit or -179 degrees Celsius. Cold enough that any exposed skin would suffer frostbite in seconds. The methane rain falling from the clouds would evaporate almost immediately off a heated spacesuit, leaving faint streaks in the frozen ground. On Europa, the surface is younger and smoother than almost anywhere else in the solar system, an icy shell crisscrossed with reddish-brown cracks, evidence of a churning ocean below, constantly reshaping the crust from underneath. Standing there, in gravity about 1/8 of Earth's, under a faint, distant sun, and the enormous, looming presence of Jupiter filling a huge portion of the sky. A person would be standing atop what might be the most promising place in the entire solar system to find life. And yet, they'd be completely unable to see it, sealed away beneath miles of ice, waiting for someone to finally drill down and look. Uranus sits at about 1.8 billion miles from the Sun, and the only spacecraft to ever visit it, Voyager 2, took about 8.5 years, using a series of gravity assists. Neptune, the outermost known planet, sits about 2.8 billion miles from the Sun, and Voyager 2 took 12 years to reach it, launching in 1977 and arriving in 1989. Neptune's largest moon, Triton, is one of the strangest bodies in the solar system, orbiting backward relative to Neptune's rotation. That's a strong hint that it wasn't born alongside the planet, but was instead captured from elsewhere, likely from the same distant, icy region as Pluto. Voyager 2's brief flyby revealed active geysers on Triton's surface, plumes of nitrogen gas erupting several miles into its thin atmosphere. Driven by sunlight, warming subsurface ice, even at that extraordinary distance from the Sun. We've only ever seen Triton up close, for a matter of hours, during a single flyby, nearly 4 decades ago. That means an entire moon, with active geology and genuine mysteries still unresolved, has essentially gone unexamined by any spacecraft for the length of most people's adult lives. Add up a full grand tour of the outer planets, with time spent at each stop and a return trip home, and you've consumed an enormous portion of a human lifetime. It's not impossible. It's just extraordinarily costly in the one resource nobody can manufacture more of: time. A single crewed mission to Neptune and back, done properly, with time to actually study the system once you arrive, could easily consume 15 to 20 years of a person's life. That's a third or more of someone's entire working adult lifetime, spent almost entirely in transit, almost entirely inside a metal container, almost entirely away from everyone and everything they've ever known. The outer planets sit right at the edge of what's practically reachable within one human life, and only if that life is dedicated almost entirely to the journey. Beyond Neptune lies the Kuiper Belt, a vast ring of icy bodies including Pluto, Eris, Makemake, and hundreds of thousands of smaller objects. Pluto sits about 3.7 billion miles from the Sun at its average distance. New Horizons, the fastest spacecraft ever launched at the time, still took 9.5 years to reach it, and that probe wasn't carrying the mass of a human crew. Even traveling at roughly 36,000 miles per hour relative to Earth at launch, one of the fastest departures from our planet ever achieved, New Horizons still spent almost a decade crossing the gap to Pluto. Its brief flyby lasted only a matter of hours, close enough to capture detailed images of icy mountains and a heart-shaped plain of frozen nitrogen, but far too quick to linger, orbit, or land. Slowing down enough to stop at Pluto would have required carrying vastly more fuel than the mission could afford. A crewed mission to Pluto, using anything resembling current or near-future propulsion, would likely take 15 to 25 years one way. Round trip, you're talking about consuming the majority of a human lifetime just to visit one distant, frozen world and come home. And Pluto is far from alone out there. Eris, discovered in 2005, is similar in size to Pluto, and it briefly caused astronomers to reconsider what actually counts as a planet. A debate that eventually led to Pluto's reclassification as a dwarf planet in 2006. Makemake and Haumea round out the group of recognized dwarf planets in the Kuiper Belt, each with their own strange characteristics. Haumea, for instance, spins so fast on its axis that it's stretched into an elongated egg-like shape rather than a sphere. Beyond the officially named bodies, the Kuiper Belt likely contains hundreds of thousands of icy objects larger than 62 miles across, along with trillions of smaller ones. They're remnants from the early solar system that never got swept up into a planet. Studying even a handful of these bodies properly, rather than just flying past them the way New Horizons did with Pluto in a matter of hours, would require an entirely different class of mission. One capable of slowing down, entering orbit, and spending real time at a target more than 3 billion miles from home. In 2017, astronomers spotted something moving through our solar system that didn't belong to it at all. It was an elongated reddish object later named Oumuamua, a Hawaiian word roughly meaning scout or messenger. It turned out to be the first confirmed object from outside our solar system ever detected passing through it. It came in fast, swung around the sun, and was already leaving again by the time we identified what it actually was. It was moving too quickly for any current spacecraft to have any realistic chance of catching up and studying it up close. A second interstellar visitor, a comet called Borisov, was spotted in 2019, confirming that objects like this pass through our solar system more regularly than anyone had previously assumed. They're tiny, wandering scraps of other star systems, drifting through interstellar space for millions or billions of years before briefly crossing paths with our own. These fleeting visitors are a reminder that the boundary of our own solar system isn't a solid wall. It's genuinely connected to the wider galaxy, even if almost everything that crosses that boundary does so far too quickly, and far too rarely, for us to ever catch up to it directly. At this point, we've essentially reached the outer edge of what's practically explorable by a human being in the flesh, using any propulsion system that exists today or is likely to exist within the next few decades. Everything beyond this point requires either radically different technology, radically different definitions of what counts as exploration, or both. Here's what lies beyond, and why it changes the entire nature of the question. Past the Kuiper Belt sits the Oort cloud, a theoretical shell of icy debris surrounding the entire solar system. It extends anywhere from about 2,000 astronomical units out to as far as 100,000, translating to somewhere between roughly 186 billion miles and over 9 trillion miles from the Sun. No spacecraft has ever reached it. Voyager 1, launched in 1977, and now the most distant human-made object in existence, is still roughly 300 years away from even reaching the inner edge of the Oort cloud, and it won't reach the outer edge for roughly 30,000 years. Read that again. 30,000 years for our farthest traveling spacecraft just to cross the outer boundary of our own solar system's gravitational neighborhood. No human being, using any propulsion technology available today, is crossing that distance in a single lifetime. We believe the Oort cloud exists largely because of where long-period comets come from. Comets like Hale-Bopp, which lit up the night sky in the 1990s, or Halley's Comet, visible from Earth roughly every 76 years, are thought to originate from this distant shell. They're occasionally nudged out of their orbits by the gravity of passing stars or the tidal pull of the galaxy itself. That sends them on journeys of thousands of years toward the inner solar system, where we briefly catch a glimpse of them before they swing back out into the darkness. The Oort cloud has never been directly observed or photographed, its existence inferred entirely from the orbits and behavior of these comets. Everything we think we know about this outermost region of our own solar system is, in a very real sense, still theoretical, pieced together from indirect evidence rather than a single confirmed image of the cloud itself. Long before reaching the Oort cloud, though both Voyager probes crossed a different, better understood boundary, called the heliopause. That's the edge of the heliosphere, a vast bubble of charged particles and magnetic field lines blown outward by the sun, which pushes back against the thin gas and radiation filling interstellar space. Voyager 1 crossed this boundary in 2012, and Voyager 2 followed in 2018, both crossings confirmed by a sudden, measurable drop in particles originating from our own sun, and a corresponding rise in cosmic rays streaming in from elsewhere in the galaxy. Crossing that boundary is often described as the moment a spacecraft truly leaves the solar system, entering the vast, mostly empty expanse of interstellar space. Technically, though, the sun's gravitational influence and the outer edge of the Oort cloud still extend enormously farther out beyond it. The Oort cloud effectively marks the true edge of what's reachable, using current chemical and ion propulsion. Beyond it lies interstellar space, and beyond that, the first star systems other than our own. This is where the entire calculation shifts from engineering to physics itself. The nearest star system to our own is Alpha Centauri, about 4.24 light-years away, for its closest member, Proxima Centauri, which translates to roughly 25 trillion miles. Voyager 1, traveling at about 38,000 miles per hour, would take approximately 75,000 years to cover that distance, if it were even aimed in that direction, which it isn't. 75,000 years is longer than the entire span of recorded human history. No chemical rocket, no ion drive, nothing built with current technology gets a human being to another star system within a single lifetime. If we're going to expand the reachable universe past our own solar system, we need propulsion that doesn't exist yet. We need propulsion capable of reaching a meaningful fraction of the speed of light. So, here's what's actually on the table, theoretically, and what it would buy us. Before diving into what's theoretically possible, it helps to know what's actually been achieved. The fastest human-made object ever built is the Parker Solar Probe, which uses repeated gravity assists from Venus to spiral closer and closer to the Sun. In the process, it gets flung to speeds exceeding 430,000 miles per hour relative to the Sun, fast enough to travel from New York to Tokyo in under a minute. Even at that record-breaking speed, still faster than anything else humanity has ever launched, it would take Parker Solar Probe's velocity, sustained indefinitely, more than 6,500 years to reach even the nearest star. That single comparison tells you almost everything you need to know about the gap between our fastest current achievement and what interstellar travel actually demands. Ion propulsion, the kind used on missions like Dawn, works by accelerating charged particles out the back of the spacecraft to produce thrust, and it's incredibly fuel efficient. But the thrust is tiny, comparable to the pressure of a piece of paper resting on your hand. Over years, that tiny thrust adds up to respectable speeds, but nowhere near what's needed for interstellar travel. A more advanced variant, called VASIMA, short for Variable Specific Impulse Magnetoplasma Rocket, uses radio waves to heat propellant into a plasma, then channels it through a magnetic nozzle to produce thrust. It's been proposed as a way to cut Mars transit times down to as little as a few months, rather than the better part of a year. But even Vasima, in its most optimistic designs, still tops out at speeds far too slow to make interstellar distances practical within a human lifetime. It would make our own solar system dramatically more accessible, potentially turning years-long outer-planet missions into journeys of a few years instead of a decade or more. But it does nothing to solve the fundamental problem of crossing light years rather than millions of miles. Nuclear thermal propulsion uses a nuclear reactor to superheat propellant and expel it for thrust, roughly doubling or tripling the efficiency of chemical rockets and cutting Mars transit times significantly. But it still tops out at speeds measured in tens of thousands of miles per hour, not the millions needed to make interstellar distances practical. Nuclear pulse propulsion, an idea first seriously studied in the 1950s and 60s under Project Orion, proposed detonating small nuclear explosives behind a spacecraft and riding the shockwave forward. The project was led by physicist Freeman Dyson and a team of engineers who took the idea seriously enough to build small-scale test models using conventional chemical explosives. Those models proved that a pusher plate could survive repeated blasts and convert them into smooth, controlled thrust rather than being torn apart. The full-scale version was never built, partly due to engineering hurdles, and partly because the Partial Test Ban Treaty of 1963 prohibited nuclear detonations in space, effectively ending serious development of the concept. On paper, this could theoretically push a spacecraft to speeds of around 3 to 10% of the speed of light. That sounds incredible until you calculate what that actually means for a trip to Alpha Centauri. At 10% of light speed, the fastest end of that theoretical range, the journey would take about 42 years. At 3%, it stretches out to around 140 years. 42 years, one way, using a propulsion method that has never been built, tested at scale, or even attempted. That's due to both engineering hurdles and the obvious problems of detonating nuclear devices near a crewed spacecraft. Fusion propulsion harnesses the same reaction that powers the Sun itself, and it's been proposed in concepts like Project Daedalus, a 1970s-era study by the British Interplanetary Society. Daedalus theorized a probe that could reach about 12% of the speed of light, cutting a hypothetical trip to a nearby star down to around 35 years. Still, no working fusion drive exists. But the physics, at least, doesn't violate any known laws. Antimatter propulsion sits at the far edge of theoretical possibility. When matter and antimatter meet, they annihilate completely, converting their entire mass into energy according to the relationship E equals mc squared. That releases far more energy per unit of fuel than any chemical or even nuclear reaction. In theory, an antimatter-powered spacecraft could reach a significant fraction of light speed, potentially even higher than fusion designs. In practice, we've only ever produced antimatter in quantities measured in nanograms, at extraordinary cost, using massive particle accelerators. The European Organization for Nuclear Research, home to the Large Hadron Collider, has managed to trap small numbers of antihydrogen atoms for scientific study, a genuine achievement in particle physics, but a staggering distance away from the kind of industrial-scale production a spacecraft would require. Even a small amount of antimatter fuel, at current production rates and costs, would represent an amount of money far exceeding the entire global economy many times over. Producing enough antimatter to fuel an interstellar mission would require industrial capabilities that don't exist and might not exist for centuries. Then there's the light sail approach, made famous by the Breakthrough Starshot initiative, which proposes launching tiny gram-scale probes attached to reflective sails, then pushing them with a ground-based laser array. The concept relies on an enormous ground-based array of individual lasers, potentially thousands of them, all fired simultaneously and focused with extreme precision onto a sail only a few yards across. A burst, lasting just a few minutes, could accelerate a probe weighing barely more than a paperclip to a meaningful fraction of the speed of light, before the laser array loses its lock and the tiny craft coasts the rest of the way on its own. The theoretical goal is to accelerate these tiny probes to around 20% of the speed of light, which would get an unmanned probe to Alpha Centauri in around 20 years. But notice the word unmanned. This technology, even in its most optimistic form, works for objects the size of a postage stamp, not for spacecraft large enough to carry, feed, and protect a human crew. Scaling it up to something that could carry people multiplies the mass by many orders of magnitude, and the power required to accelerate that mass to relativistic speeds grows right alongside it. There's one more idea, stranger than all the others, that occasionally gets raised in serious physics circles rather than just science fiction. In 1994, physicist Miguel Alcubierre proposed a mathematical solution within Einstein's own equations, describing a way to move a region of space itself rather than moving an object through space. The idea involves contracting space in front of a ship and expanding it behind, creating a kind of wave that the ship rides. Since the ship itself never locally exceeds the speed of light, and it's the space around it that's doing the moving. On paper, this doesn't violate relativity at all, since relativity only limits how fast things can move through space, not how fast space itself can expand or contract. We already know that happens, since the universe's own expansion regularly carries distant galaxies away from us faster than light in exactly this way. In 2024, a research team published updated mathematics suggesting a version of this concept that wouldn't require negative energy. Negative energy would need to have less than zero mass, and as far as we know, it doesn't exist anywhere in measurable quantities. It's a genuinely exciting development in theoretical physics. It is not, however, anywhere close to an engineering blueprint. The energy requirements, even in the most optimistic updated calculations, remain staggering, and no laboratory on Earth has ever created, measured, or manipulated the kind of exotic conditions such a drive would require. It remains a fascinating gap in our understanding. It's a door that mathematics says might not be permanently sealed, rather than a technology anyone alive today will ever climb aboard. Every single one of these propulsion concepts, even in their best case, most optimistic, still theoretical forms, gets us to maybe 10 to 20% of the speed of light. And that ceiling changes everything about how we need to think about this problem. Because now we have to bring in one more piece of physics that most people don't consider until it's forced on them. Time itself doesn't move the same way for everyone, and Einstein's theory of special relativity tells us that as an object approaches the speed of light, time for that object, relative to a stationary observer, slows down. This isn't science fiction. It's been measured directly, using atomic clocks flown on airplanes, using particles in accelerators, using the extraordinarily precise clocks on GPS satellites. Those satellite clocks have to be corrected for this effect every single day, or the entire system would drift into uselessness within hours. At 10% of the speed of light, the effect is small but real, time slowing by less than 1% for the traveler. At 50% of the speed of light, a clock on board a moving spacecraft runs about 13% slower than a clock left behind on Earth. At 90% of the speed of light, time slows by more than half. At 99%, a single year on board the ship corresponds to about 7 years back home. Physicists sometimes illustrate this with what's called the twin paradox. Imagine two identical twins. One stays on Earth, living an ordinary life, aging normally year after year. The other boards a spacecraft capable of reaching a significant fraction of the speed of light, travels to a distant star, turns around, and comes back. When the traveling twin finally steps off the ship, they find their sibling has aged far more than they have. Depending on how close to light speed the ship traveled, and for how long, the traveling twin might return to find decades have passed on Earth, while they themselves aged only a handful of years. This isn't a paradox in the sense of being a contradiction. It's a genuine, measured, repeatedly confirmed feature of how time and motion are linked together in our universe. It's been verified using precise atomic clocks flown on commercial airliners, which, after circling the globe, showed a measurable, predicted difference compared to identical clocks left on the ground. It's also built directly into technology billions of people rely on every single day without realizing it. GPS satellites orbit Earth at high speed while also sitting farther from Earth's gravity than we do on the surface. Both of those factors affect how quickly their onboard clocks tick compared to clocks down here. One effect comes from their velocity, another from the weaker gravity at their altitude, and the two don't fully cancel out. Left uncorrected, that combined drift would cause GPS positioning errors of several miles within a single day. That's why the satellite's clocks are deliberately engineered to run at a slightly different rate before launch, precisely compensating for relativity's effects. That way, the navigation system in your phone or car actually points to the right street rather than one several miles away. The effect at airliner speeds is minuscule, a matter of nanoseconds. But it's there, and it scales upward dramatically as speeds approach light itself. This is where the story gets genuinely strange and genuinely important for our question. And it matters a great deal, because the destinations worth reaching aren't purely hypothetical anymore. Astronomers have now confirmed thousands of planets orbiting other stars, and a meaningful number of them sit within what's called the habitable zone, the range of distance from a star where temperatures could allow liquid water to exist on a planet's surface. Much of this catalogue comes from a single, remarkably productive space telescope called Kepler, launched in 2009. It stared continuously at a single patch of sky for years, watching for the tiny, repeating dip in a star's brightness caused by a planet passing directly in front of it. That patient, methodical technique confirmed the existence of more than 2,600 planets on its own. It also revealed something genuinely surprising, that planets are not rare at all. On average, most stars in our galaxy likely host at least one planet of their own, which transformed exoplanets almost overnight from a handful of exotic discoveries into an expected, ordinary feature of the universe. The TRAPPIST-1 system, about 40 light-years away, contains 7 roughly Earth-sized planets orbiting a small, cool red dwarf star. As many as 3 of them sit within that habitable zone, close enough together that if you stood on the surface of one, the others would appear as visible disks in the sky, sometimes larger than our own moon appears from Earth. Proxima Centauri, the nearest star to our own, was found in 2016 to host a planet roughly Earth-sized, orbiting well within its habitable zone, meaning our very nearest stellar neighbor might also be our nearest, genuinely Earth-like world. It's a tantalizing thought, given everything we've just learned about how far 4.24 light-years actually is. Later observations even hinted at the possibility of a second, smaller planet in the same system, though confirming its existence and properties has proven difficult, given how faint and close to its star any such world would be. It's a reminder that even our closest neighboring system still guards many of its secrets from telescopes alone. These worlds give the entire propulsion and time dilation conversation somewhere to actually point toward, real coordinates rather than abstract math. They're real possible destinations that give the question of interstellar travel an actual sense of purpose rather than pure theory. Because if we could ever build a spacecraft capable of sustained acceleration toward relativistic speeds, the crew on board wouldn't experience the full weight of interstellar distances the way an outside observer would. To someone watching from Earth, a ship traveling to a star 100 light-years away, even moving at 99% of light speed, would still take just over 100 years to get there. But to the crew on board that ship, thanks to time dilation, the journey might only feel like 14 years. The faster you go, the more the universe seems to compress in front of you, from your own point of view. This means the reachable universe, defined by what a human traveler could experience within their own subjective lifetime, is actually much larger than what pure distance and a fixed speed limit would suggest. Theoretically, with continuous acceleration at a comfortable 1g, roughly the same acceleration you feel from Earth's gravity, the math gets remarkable. Assuming you could maintain that acceleration for years without running out of fuel or destroying the ship. Using calculations based on relativistic rocket equations, a ship accelerating at 1g for the first half of a journey and decelerating at 1g for the second half could, in theory, reach a star 10 light-years away in about 12 years of subjective time on board. A star 100 light-years away might take around 22 years of subjective onboard time. A star 1,000 light-years away might take around 29 years of subjective onboard time. The relationship isn't linear. As speeds get closer and closer to the speed of light, and time dilation gets more and more extreme, you can theoretically cross vastly greater distances without the subjective, felt time increasing nearly as much. Picture what that acceleration would actually feel like from inside the ship. For the first year, you'd feel exactly as heavy as you do standing on Earth right now, pressed gently into your seat by the ship's engines rather than by gravity. By the end of that first year, still accelerating at a steady 1g, you'd already be moving at a meaningful fraction of the speed of light relative to Earth. By the second year, you'd be closing in on speeds where the strange effects of relativity become noticeable. Distant stars ahead of you would appear to shift color, compressing toward blue, while stars behind you would shift toward red. That effect is called relativistic aberration, and it would change the entire visible sky into something that no longer resembles the night sky you grew up under. Halfway through the journey, the ship would flip around and begin decelerating at the same steady 1g, so that by the time you arrived at your destination, you'd be moving slowly enough to actually stop, rather than shooting past it at a meaningful fraction of light speed. The entire experience, from your own point of view, watching your own clock, would feel like a normal, if very long, multi-year voyage. It's only when you compared your ship's clock to the one you left behind on Earth that the strangeness of the whole thing would become impossible to ignore. Push the math far enough, and a sufficiently advanced, continuously accelerating spacecraft could, in theory, cross tens of thousands of light years within a single human lifetime, as experienced by the crew on board. That sounds like it solves the problem. It doesn't. Because there's a catch, and it's an enormous one. While time on board the ship might only pass by 20 or 30 years, time back on Earth, and at the destination, keeps moving at its normal pace. A crew that travels 100 light years and experiences only 22 years passing would return, if they returned at all, to find that over 200 years had passed at home. Everyone they knew would be gone. The civilization they left would have changed beyond recognition, assuming it still existed at all. This isn't exploration in any sense that lets you come home and report what you found to the people who sent you. It's a one-way trip into someone else's future. And that raises the real philosophical wall standing behind the physical one. Is a journey like that still exploration in the way we normally mean the word? Or is it something else entirely? A kind of voluntary exile into deep time, where the explorer's own past becomes as unreachable as any distant star. There's also the small matter that none of the propulsion technology needed for sustained 1G acceleration over years actually exists. Every theoretical design we have, nuclear pulse, fusion, antimatter, light sails, tops out at a fraction of light speed and then coasts, rather than continuously accelerating the entire way. Continuous acceleration at 1G for years requires almost unimaginable amounts of energy and propellant, demanding fuel to mass ratios that current physics and engineering can't come close to achieving. So, while the mathematics of relativistic time dilation genuinely does expand the theoretical reachable universe for a human traveler, the propulsion technology needed to actually exploit that expansion doesn't exist. It might not exist for centuries, if ever. There's another obstacle standing in the way that has nothing to do with propulsion or relativity, and everything to do with basic human biology: radiation. Once you leave the protection of Earth's magnetic field and thick atmosphere, you're exposed to a constant bombardment of galactic cosmic rays and solar particles. Earth's magnetic field, generated by the churning motion of molten iron deep in our planet's core, extends far out into space, deflecting the vast majority of charged particles that would otherwise strike the surface directly. Some of those particles get funneled toward the poles instead, where they collide with the atmosphere and produce the shimmering aurora that people travel great distances just to witness. Mars, by contrast, lost its own global magnetic field billions of years ago. Part of why its atmosphere has been slowly stripped away by the solar wind ever since, leaving it with barely 1% of Earth's atmospheric pressure and almost none of Earth's radiation protection. It's a preview of exactly the kind of exposed, unshielded environment that any spacecraft traveling beyond Earth's magnetosphere has to contend with for the entire duration of its journey. Astronauts on the International Space Station, still well within Earth's protective magnetosphere, absorb radiation doses many times higher than people on the ground. A journey to Mars alone would expose a crew to a significant fraction of their entire career radiation limit, raising long-term cancer risk substantially. A multi-year journey to the outer solar system multiplies that exposure many times over. An interstellar journey lasting decades, even with time dilation reducing the subjective time experienced, still means decades of continuous exposure to a radiation environment far harsher than anything humans evolved to survive. Shielding helps, but heavy shielding adds enormous mass, and mass is the enemy of every propulsion system we've discussed, because more mass requires more fuel, which requires more mass to carry that fuel, in a spiral that quickly becomes unmanageable. We actually have real, measured data on some of these effects thanks to an unusual natural experiment. Astronaut Scott Kelly spent almost a full year aboard the International Space Station, while his identical twin brother, Mark Kelly, also a former astronaut, remained on Earth. Because they share identical genetics, researchers had a rare opportunity to compare the biological effects of long-duration spaceflight directly, twin against twin. They found changes in gene expression, shifts in gut bacteria, thickening of artery walls, and changes in the length of telomeres, the protective caps on the ends of chromosomes that are closely tied to aging. Most of these changes reversed within months of Scott's return to Earth, but some, including certain gene expression changes and cognitive performance on tasks requiring speed and accuracy, showed effects that lingered longer. And that was after less than 1 year in low Earth orbit, still protected by most of Earth's magnetic field. A journey lasting a decade or more, fully exposed to interplanetary and interstellar radiation, would push far beyond anything we've ever directly studied in a human being. Some researchers have proposed a way around at least part of this problem, borrowed from an unlikely source: hibernating animals. Certain mammals, like ground squirrels and bears, are able to dramatically lower their body temperature, heart rate, and metabolism for months at a time, entering a state called torpor that allows them to survive winters without eating. And it also appears to protect their bodies from some of the wear and tear that long-term inactivity would otherwise cause. Space agencies have funded early research into whether something similar could ever be induced safely in humans, since a crew in a deep, medically induced torpor might require less food, less water, less living space, and might even suffer less bone density loss and psychological strain than a crew fully conscious for years at a stretch. The research is still extremely early, mostly limited to small animal studies and theoretical models, and inducing safe, reversible torpor in a human being for months or years at a time remains far beyond current medical capability. There are added benefits too, beyond the purely physical, since a crew spending most of a multi-year journey in induced torpor would experience far less of the isolation and monotony that make long-duration missions so psychologically demanding. They'd effectively sleep through the most tedious, empty stretch of the trip and wake closer to the destination, rather than enduring years of confined, uneventful transit while fully conscious. But if it ever became possible, it wouldn't change the physics of the journey itself, and the ship would still take just as long to get there. It might, though, make the biological cost of actually surviving that journey significantly more manageable, turning years of grinding physical and psychological deterioration into something closer to a long, medically monitored sleep. Then there's the physical toll of long-duration weightlessness. Unless the ship provides artificial gravity through rotation or constant acceleration. Bone density loss, muscle atrophy, cardiovascular changes, and vision problems caused by fluid shifts in the body have all been documented in astronauts who've spent a year or more in orbit. Stretch that out to a decade or more, and the physical toll becomes severe, potentially crippling, even with the best exercise regimens and countermeasures we can currently design. And then there's the psychological weight of it. Isolation. Confined space. No ability to leave, no fresh air, no open sky, for years or decades at a time. The people you started the journey with become the only human contact you'll have for the rest of your life. We already have some sense of what extended isolation does to a crew, thanks to analog environments here on Earth. Researchers stationed at Antarctic outposts, particularly those who stay through the long, dark polar winter when no flights can land and evacuation becomes essentially impossible, have reported symptoms researchers now call the winter over syndrome. That includes depression, irritability, difficulty concentrating, and disrupted sleep, all triggered simply by months of isolation, confinement, and limited sunlight. In an environment far less hostile and far more reachable than deep space. Simulated Mars missions have documented similar patterns, including multi-month isolation studies, where volunteer crews live inside sealed habitats designed to mimic the constraints of a real mission, showing growing interpersonal tension as the mission stretches on. The same small group of people are forced to rely entirely on each other, day after day, with no outside contact beyond delayed, scheduled communication. And communication delay itself becomes a genuine psychological burden the farther you travel. A radio signal from Mars takes anywhere from about 4 to 24 minutes to reach Earth, depending on the planet's positions, meaning a real-time conversation is simply impossible. Every exchange becomes a question and a long wait for the reply. At the distance of the outer planets, that delay stretches to hours. At interstellar distances, even communicating at the speed of light, a message sent home would take years just to arrive. Any reply would take years more. A crew traveling to another star system would, for all practical purposes, be completely cut off from real-time contact with Earth for the rest of the mission, receiving only an increasingly outdated stream of messages from a world that kept moving on without them. And underlying every part of this is a simpler, blunter risk that grows with every year a mission stays in transit. Something breaking. A life support failure. A micrometeorite puncturing the hull. A software error in a system with no engineer nearby capable of repairing it. Any single point of failure sustained across a journey lasting years or decades becomes statistically far more likely to eventually occur, simply because there's so much more time for something to go wrong. On the International Space Station, orbiting just a few hundred miles above Earth, resupply missions and emergency return capsules are available on relatively short notice if something fails. A crew traveling to the outer planets or beyond has no such option. Whatever breaks has to be fixed with whatever's on board, using whatever spare parts and expertise happen to be present, or the crew has to find a way to survive without it, for the remainder of a journey that might still have years left to run. Every additional year of mission length isn't just an additional year of radiation exposure and psychological strain. It's an additional year of accumulated risk that something, anything, critical to survival, simply fails, with no possibility of rescue. We haven't solved even one of them completely. Which is why, when we're being honest about it, the reachable universe for an actual human being, in the flesh, within a single lifetime, doesn't extend past our own solar system, using anything we can currently build or reasonably expect to build within the next several decades. It stops somewhere around Neptune, or the inner edge of the Kuiper Belt, if you're willing to dedicate the majority of your working life to getting there and back. There's one more idea worth considering before we move past the question of human bodies crossing interstellar distances. It approaches the problem from a completely different angle. Instead of trying to get one person there fast, What if you simply accepted that the journey would take generations? You'd send enough people to keep a functioning, self-sustaining society alive for the entire trip. This is the concept behind generation ships, massive vessels designed to carry thousands of people on journeys lasting centuries. The crew who launches will never see the destination. Only their distant descendants, born and raised entirely within the ship, will actually arrive. At speeds achievable with near-future technology, say 1 or 2% of the speed of light, a journey to even the nearest star system would take somewhere between 2 and 4 centuries. That's roughly 10 to 15 human generations, living, working, raising children, growing old, and passing away, all inside a sealed, artificial environment, traveling through the emptiness between stars. The ship would need to be entirely self-sufficient. It would need to grow its own food and recycle its own air and water indefinitely. It would need to maintain its own systems with no possibility of resupply or rescue from Earth. And it would somehow need to preserve enough genetic diversity across generations to avoid the serious health problems that come from a population that's too small and too isolated. Population geneticists who've studied this problem generally estimate that a genuinely sustainable, multi-generational population would need to start with several thousand people at an absolute minimum. That's 1. Avoiding the compounding health effects of inbreeding over dozens of generations. And some estimates run considerably higher, depending on how strictly you want to preserve genetic health over centuries rather than mere decades. That number alone reshapes what a generation ship would actually need to be. Not a small crew capsule, but something closer to a small floating city. It would need hospitals, schools, farms, and enough redundant infrastructure to keep several thousand people alive and reasonably healthy for the entire multi-century duration of the voyage. It would also need to somehow maintain enough social stability, enough shared purpose across centuries and dozens of generations for the mission to actually survive to completion. Otherwise, it risks drifting away from its original goal or collapsing entirely under the psychological weight of permanent confinement. Serious proposals for what such a ship might actually look like often draw on designs originally conceived for permanent space habitats closer to home, like the O'Neill cylinder, a concept from the 1970s involving a rotating cylindrical structure, potentially miles long. It spins to create artificial gravity along its inner surface through centrifugal force, with strips of simulated landscape, agriculture, and living space lining the interior walls. Scale that concept up. Add shielding thick enough to block cosmic radiation over centuries rather than years. Add enough redundancy in every life support system to survive equipment failures with no possibility of resupply from Earth. And you begin to approach what an actual generation ship might require: a self-contained, spinning world, small compared to a planet, but permanent enough to be the only home multiple generations would ever know. History offers a cautionary parallel, even if an imperfect one. Long ocean voyages in earlier centuries, isolated naval postings, and even some early polar expeditions have all documented cases of crews fracturing under prolonged confinement. Mutinies, factional splits, and complete breakdowns of the original chain of command, all triggered by months, not centuries, of isolation from the wider world. Scaling that same fundamental challenge up to a timescale of hundreds of years and multiple generations who never chose their circumstances in the first place, represents a social and psychological engineering problem. It may ultimately prove just as difficult to solve as the propulsion required to make the journey in the first place. No one born partway through the journey would have chosen to be there. They would simply be born into a mission decided by ancestors they never met, traveling toward a destination they might not live to see either. It's a genuinely unsettling thought, one that highlights something important about the difference between what's physically possible and what's actually reasonable to attempt. Generation ships solve the propulsion and time dilation problem in theory, but they trade it for an entirely different kind of cost. One measured not in fuel or years, but in generations of human lives lived entirely in transit, never setting foot anywhere but the metal corridors of the ship itself. Whether humanity ever attempts something like this remains an open question, one that depends less on engineering and more on what we're collectively willing to ask of people who never got a vote in the matter. So does that mean the rest of the universe is simply off limits to exploration, permanently, forever? Not exactly. Because exploration doesn't require a human body to be physically present at the destination, and robotic probes have already expanded humanity's reach far beyond what any person will see with their own eyes in this century. Voyager 1 and Voyager 2, launched in 1977, have both left the heliosphere, the bubble of charged particles blown outward by our sun, and entered interstellar space. They are, right now, the farthest human-made objects from Earth, and they carry with them a golden record, a message in case anything or anyone out there ever finds them. That record includes recordings of natural sounds from Earth, greetings spoken in dozens of languages, and a curated selection of music, along with encoded images showing our solar system, human anatomy, and daily life, all etched onto a gold-plated copper disc designed to remain readable for well over 1 billion years. It's a message sent with essentially no expectation of ever reaching an audience, but sent anyway, as a quiet gesture across an ocean of empty space. New Horizons gave us our first close look at Pluto and continues onward through the Kuiper Belt. Parker's solar probe has flown closer to the Sun than anything humans have ever built, directly sampling the outer solar atmosphere. The Cassini-Huygens mission dropped a probe onto the surface of Titan in 2005, giving us the only images ever taken from the surface of a moon in the outer solar system. A landscape of ice boulders sitting in a dry riverbed shaped by liquid methane rather than water. The Rosetta mission chased down a comet, entered orbit around it, and released a small lander named Philae, which touched down on its surface in 2014, the first time any spacecraft had ever soft-landed on a comet's nucleus. The landing didn't go entirely as planned. Philae's anchoring harpoons failed to fire, and the lander bounced twice across the comet's surface before finally settling in a shadowed crevice where its solar panels couldn't gather enough sunlight to keep it powered for long. But in the brief window before its batteries ran out, it still managed to transmit valuable data about the comet's composition. It was a small, imperfect, but genuinely historic first for humanity's reach into the solar system. The Curiosity and Perseverance rovers have been crawling across the surface of Mars for years at a time, drilling into rock, analyzing soil chemistry, and, in Perseverance's case, collecting samples that a future mission is intended to eventually bring back to Earth. Curiosity alone has been operating on Mars for well over a decade now, far outlasting its original planned mission length of just under 2 Earth years. It's a reminder that even robotic exploration, freed from the biological limits of a human crew, still tends to exceed every original estimate. Simply because there's always more worth investigating once a mission actually arrives somewhere new. Each of these missions extended human knowledge across distances and into environments that no person could currently survive visiting directly, which is precisely why every serious plan for eventually sending humans anywhere new starts with robots first. A robotic probe doesn't need air, water, food, radiation shielding thick enough to protect soft tissue, or any hope of returning home. It can be exposed to lethal radiation doses, extreme temperatures, and years of total isolation without any of the biological or psychological consequences that would end a human life or a human mind. It can also, frankly, be risked. If a probe fails, a mission is lost, funding is wasted, and scientists are disappointed. But no one dies. That distinction alone explains why humanity's reach as a species, expressed through cameras and instruments rather than through living bodies, extends so much farther than our reach as individual explorers ever could, and likely always will, until propulsion, technology, and radiation shielding both advance dramatically beyond where they currently stand. Which raises an honest question. If robots can go farther, survive harsher conditions, and cost far fewer lives, why does humanity still insist on sending people at all? Every space agency that has ever studied this question has arrived at roughly the same answer. Robots are extraordinary tools, but they lack judgment and adaptability. They lack the ability to notice something unexpected and immediately understand why it matters. That's the kind of intuitive leap a trained human scientist can make standing in front of an unusual rock formation. A leap that a probe, however sophisticated its programming, still struggles to replicate. There's also something harder to quantify. It's a reason space agencies rarely put into official mission justifications, but that shows up again and again in the words of astronauts themselves. The experience of actually being there, of seeing Earth as a small, fragile point of light from a great distance, of setting foot somewhere no human has ever stood, changes people in ways that watching a photograph never quite manages to do. That shift in perspective, carried back to billions of people who will never leave Earth themselves, has its own kind of value. It's difficult to put a dollar figure on, but real all the same. These missions, and dozens of others, represent humanity's true current reach. They extend not through human bodies, enduring the radiation and isolation of deep space, but through machines built to endure conditions no person could survive. There's also a third category to consider, one that expands our knowledge without sending anything anywhere at all: telescopes. The James Webb Space Telescope, orbiting nearly 1 million miles from Earth, has photographed galaxies whose light left them more than 13 billion years ago, capturing them as they appeared when the universe itself was still in its infancy. It has directly analyzed the atmospheres of planets orbiting other stars, identifying water vapor, carbon dioxide, and other molecules in worlds we will, in all likelihood, never physically visit, not with any technology available to us now or for a very long time afterward. Future telescopes, currently in development, aim to go even further, searching not just for water vapor and carbon dioxide, but for combinations of gases in a planet's atmosphere that, on Earth, are only produced by living organisms. Oxygen, alongside methane, for example, is a pairing that tends to react and disappear quickly unless something is continuously replenishing it, the way plants and microbes replenish it here. Finding such a signature on a distant world wouldn't prove life exists there with absolute certainty, but it would represent the strongest evidence yet gathered without ever leaving our own solar system, evidence collected entirely through starlight. filtered and analyzed across trillions of miles of empty space. In a real sense, telescopes let us explore the parts of the universe that will remain forever physically unreachable, not by traveling there, but by capturing the light that traveled here for us. Across distances and times so vast that the light itself becomes a kind of time capsule, showing us places as they existed long before Earth even had an atmosphere capable of supporting life. It's not the same kind of exploration as standing on a moon of Jupiter or drilling into the ice of Europa, but it's real knowledge, real discovery, extending our reach across a universe that our bodies will never physically cross. In that sense, the exploration boundary and the human boundary are two very different lines. Robotically, we've already touched every planet in the solar system. We've landed on Mars, on Venus, on Titan, on a comet, on an asteroid. We've sent instruments beyond the edge of the solar wind's influence. We've photographed nearly every major moon in the outer solar system in detail. If you define exploration as extending human knowledge and human presence through the instruments we build and the data we bring home, then our reachable universe is enormously larger than the bubble a human body could physically survive crossing. But here's where the scale gets truly humbling, because the question of how much of the universe deserves a true, honest sense of scale, not just a solar system's worth of it. Our galaxy, the Milky Way, is roughly 100,000 light-years across, containing somewhere between 100 billion and 400 billion stars. Even using our most optimistic, entirely theoretical, relativistic propulsion, sustained at 1g acceleration for the entire journey, reaching the far side of our own galaxy would take somewhere in the range of 12 years of subjective onboard time to accelerate and cross a meaningful fraction of it. But the round trip and any hope of returning to a civilization you'd recognize would be utterly impossible. By the time you got back, hundreds of thousands of years would have passed on Earth. There would be no returning, no reporting your findings, no continuity with the world you left. Our solar system sits inside one of the Milky Way's spiral arms, roughly 26,000 light-years from the galactic center, a region dominated by a supermassive black hole called Sagittarius A, with a mass equivalent to about 4 million times that of our Sun. Astronomers have directly imaged the glowing ring of material swirling around it, confirming decades of indirect evidence that it exists. Reaching the galactic center, even with our best theoretical propulsion and the most generous application of time dilation, would mean crossing a region of space far more crowded and far more energetic than the quiet neighborhood we currently call home, filled with intense radiation, densely packed stars, and gravitational forces unlike anything in our own solar system. It's a genuinely fascinating place to imagine visiting. It's also, for all practical purposes, permanently beyond anything a human explorer could ever reach and return from. To put the scale of our own galaxy into perspective, if you tried to count every star in the Milky Way, one per second, without stopping to eat or sleep, it would take you somewhere between 3,000 and 12,000 years, depending on which current estimate of the galaxy's total star count you use. And the Milky Way is considered a fairly typical, mid-sized spiral galaxy, while some galaxies contain trillions of stars. Every single one of those stars is, in principle, a potential destination, a potential sun for some other world, and the overwhelming majority of them will never be visited by anything originating from Earth, not by a human, and quite possibly not even by a robotic probe. There simply isn't enough time in the remaining life of our sun, let alone a single human lifetime, to reach more than a vanishingly small handful of them. Beyond our galaxy lies the local group, a collection of over 50 galaxies, including Andromeda, our nearest large galactic neighbor, sitting about 2.5 million light-years away. Andromeda is actually on a likely collision course with our own galaxy, drawn together by mutual gravity. And if that collision happens, it's expected sometime in the next 4 to 10 billion years, long after our Sun will have already changed dramatically as it nears the end of its own life. Recent studies, using updated satellite data, have actually introduced real uncertainty into that timeline, putting the odds of an eventual direct merger at something closer to a coin flip rather than a settled certainty. If and when that merger happens, it won't look like a violent collision in the way the word might suggest, since the distances between individual stars within each galaxy are so enormous that direct star-to-star collisions will be exceedingly rare. Should the two galaxies collide, they'd slowly pass through and around each other over hundreds of millions of years, their gravity reshaping both into a single, larger, elliptical galaxy, a process astronomers have already modeled in detail using observations of similar mergers happening elsewhere in the universe right now. Even Andromeda, our single, closest large galactic neighbor, sits so far beyond anything achievable by even the most optimistic, relativistic, propulsion and time dilation calculations that reaching it simply isn't on the table. Not in any meaningful sense involving return or continuity with the civilization that sent you, not with physics as we currently understand it, and likely not ever. Beyond the local group lies the observable universe itself, a sphere roughly 93 billion light-years across, once estimated to contain as many as 2 trillion galaxies, though more recent analysis suggests the real number is likely much smaller, possibly closer to a few hundred billion, each still containing hundreds of billions of stars of its own. Now here's where the final, hardest wall of the entire question appears, and it has nothing to do with propulsion, relativity, or biology. The universe is expanding. Not just expanding, but accelerating in its expansion, driven by something we call dark energy, a force we still don't fully understand, but have measured with tremendous precision. This was first discovered by astronomer Edwin Hubble in the 1920s, when he noticed that distant galaxies all showed light shifted toward the red end of the spectrum. The more distant a galaxy was, the more its light was shifted, and this relationship, now called Hubble's law, revealed that galaxies aren't just scattered randomly through static space. They're all moving away from each other as space itself stretches, like dots painted on the surface of a balloon that's being inflated. Decades later, in the late 1990s, 2 independent teams of astronomers studying distant exploding stars, called supernovae, discovered something even stranger. The expansion wasn't just continuing, it was speeding up. It was accelerating over cosmic time, rather than slowing down under the pull of gravity the way everyone had expected. That discovery earned the astronomers involved the Nobel Prize in Physics in 2011. It forced scientists to conclude that roughly 70% of the universe's total energy content consists of this mysterious dark energy, a property of space itself that pushes everything apart at an ever-increasing rate. We can also see the afterglow of the universe's earliest moment, called the cosmic microwave background. It's a faint glow of radiation left over from when the universe was only about 380,000 years old, now stretched by billions of years of expansion into faint microwave radiation detectable in every direction we look. It's the oldest light we can possibly observe. Studying its tiny variations in temperature has told us an enormous amount about the age, composition, and geometry of the universe as a whole. Because of this expansion, most of the galaxies we can currently see are moving away from us. The farther away a galaxy is, the faster it appears to recede. Beyond a certain distance, galaxies are receding faster than light itself. That's not because anything is moving faster than light locally, but because the space between us and them is stretching so quickly that light from those galaxies will never be able to cross the growing gap to reach us. Nothing we send will ever be able to cross it to reach them either. This defines something astronomers call the cosmic event horizon, roughly 16 billion light-years away in today's terms. That number itself keeps growing as expansion continues. The boundary of what's permanently unreachable isn't fixed. It's actively expanding outward over time, quietly placing more and more of the universe forever beyond reach with every passing year. It's a slow, one-directional process that has been running since long before Earth existed and will continue long after. Galaxies beyond that horizon are not just unreachable. They are permanently, physically disconnected from us in a way that no propulsion technology, no relativistic trick, no amount of time could ever overcome. Even light, the fastest thing in existence, will never bridge that gap. So, the true, reachable universe, even in the most generous, most theoretical, most optimistic sense, imagining technology we don't have and may never develop, is bounded by that horizon. Everything beyond it exists, as far as we can tell, but it's forever beyond the reach of anything originating from Earth, for all time. This same set of limits, the speed of light, the scale of a galaxy, the short span of a biological lifetime, happens to be one of the leading explanations for a puzzle physicists call the Fermi paradox. It's named after physicist Enrico Fermi, who once asked a simple question during a lunchtime conversation in 1950. Given how many stars exist, how many of them likely host planets, and how old the universe already is, where is everybody? If intelligent life is even moderately common, we might expect to see some evidence of it by now. Some signal, some structure, some sign of a civilization spreading outward the way we imagine our own descendants someday might. Instead, as far as we can tell, the universe appears silent. Part of the answer may simply be exactly what we've spent this entire exploration mapping out. Even a civilization far more advanced than our own would still be bound by the same speed of light, the same vast distances between stars, the same brutal mismatch between a biological lifespan and the scale of a galaxy. Any civilization out there, wondering the same things we're wondering tonight, staring up at their own night sky, might be facing the exact same wall we are. A universe that's magnificent to look at and almost entirely unreachable to visit. Some researchers have taken this idea a step further, proposing what's called the Great Filter, the idea that somewhere along the path from simple chemistry to a civilization capable of spreading across the stars, there exists some enormously difficult barrier that very few, if any, forms of life ever manage to cross. That filter could lie behind us, in the sheer improbability of life even beginning in the first place. Or it could lie ahead of us, in the form of some catastrophe, self-inflicted or otherwise, that tends to end civilizations before they ever become capable of true interstellar travel. Tonight's entire exploration suggests a third possibility, less dramatic, but no less significant. The filter isn't a catastrophe at all. It's simply the unforgiving combination of finite lifespans and a speed of light that refuses to budge. That's a barrier, built directly into the physical laws of the universe itself, one that every sufficiently curious species eventually runs directly into, without exception. That's not necessarily a lonely thought. It might just mean that every civilization capable of asking this question is, in its own way, stuck admiring a horizon it can never fully cross. And that makes the small, reachable bubble each of us actually gets to explore all the more worth cherishing. So, here's what all of that comes down to: something a single human life can actually hold on to. With current and realistically near-future technology, the reachable universe for an actual human explorer, someone who leaves, experiences a destination, and potentially returns, extends to the edges of our own solar system. The Moon, easily. Mars, with real difficulty, but real feasibility. The asteroid belt and the large moons of the outer planets, at the cost of years of a person's life. The outer planets themselves, at the cost of a decade or more. That essentially demands that exploration becomes someone's entire life's work rather than a single mission among many. The Oort cloud and beyond, using anything we can currently build, simply isn't on the table within one lifetime. With propulsion technology that exists only on paper today, theoretical fusion and antimatter drives, sustained relativistic acceleration, the reachable universe could theoretically expand to include nearby star systems. With extreme optimism about the mathematics of time dilation, it could potentially even include a meaningful slice of our own galaxy, from the traveler's own subjective point of view. But that expansion comes at the cost of everything and everyone left behind, a one-way journey into a future none of us will recognize. And no matter how advanced our propulsion ever becomes, no matter how close to light speed we manage to push a spacecraft, no matter how cleverly we exploit the strange mathematics of relativity, there is a hard boundary, drawn by the expansion of space itself, past which nothing will ever reach, ever, for the rest of time. The universe, it turns out, isn't just big. It's structured in a way that guarantees most of it will remain forever theoretical to us. Forever a set of numbers and photographs, and light captured from an unimaginably distant past. Never a place any human foot will touch, never a place any human eye will see in person. And somehow, that doesn't make the question smaller. It makes the answer more remarkable. Because within that tiny, almost insignificant bubble we can actually reach, our own solar system, and maybe, just maybe, a handful of the nearest stars if we ever solve the propulsion problem. There are more mountains, more oceans, more canyons, more moons, more mysteries than any single human lifetime could ever fully explore anyway. Mars alone has a canyon system so vast it would stretch across the entire continental United States. Jupiter's moon Europa likely holds an ocean of liquid water beneath its icy crust, containing more water than every ocean on Earth combined. Saturn's moon Titan has lakes and rivers, not of water, but of liquid methane and ethane, under a hazy orange sky. And underneath almost every mission we've discussed tonight sits the same quiet motivation: the search for an answer to one of the oldest questions humans have ever asked. Are we alone? Harlow, Europa's hidden ocean, Enceladus's icy geysers, Titan's strange methane lakes, and even the ancient, dried-up riverbeds on Mars. Every one of these destinations earns its priority, partly because each represents a real, scientifically grounded chance of finding some form of life, even simple microbial life, existing somewhere other than Earth. Finding it wouldn't require reaching another star system at all, since it could happen inside our own reachable bubble within a single human lifetime, using missions we're already capable of planning today. That possibility alone reframes the entire conversation. The question was never really whether the wider universe is reachable. Most of it clearly isn't, and probably never will be. The real question is whether the answers we're most desperate to find. Are we alone? Is Earth truly unique? What else is out there might already be sitting within the small, dusty, icy neighborhood we happen to call our own solar system. Close enough to reach, close enough to touch, within the span of one determined human life. Even if we never leave this solar system, even if the stars remain permanently out of reach for human bodies, the bubble we can touch is so rich, so strange, and so full of genuine discovery that running out of things worth exploring was never actually the risk. The risk was always time. 50 working years against distances measured in years and decades and centuries. There's something almost paradoxical buried in all of this. The universe is, by every measure we have, staggeringly, almost incomprehensibly large. 93 billion light-years across, just in the portion we can currently observe, home to hundreds of billions of galaxies, each containing hundreds of billions of stars. And yet, the portion of it any single human being could genuinely explore, touch, walk across, study, up close, within the span of one working lifetime, is smaller than a single grain of sand would be compared to the size of an entire ocean. That's not a discouraging thought once you actually sit with it. It's a clarifying one. It means every mile, every crater, every ice-covered ocean, every methane lake, every canyon within our own small reachable bubble carries a weight and a value that easy, unlimited access would have completely erased. If we could simply hop from star to star, the way science fiction often imagines, casually, in an afternoon, the discoveries waiting out there would lose some of the very thing that makes them worth chasing in the first place. The enormous cost, the genuine risk, the years of a human life willingly spent to get there. Every civilization that has ever looked up and wondered what's out there has had to reckon with the same brutal arithmetic we've walked through tonight. The same speed limit, the same short lifespan, the same impossibly vast distances. And every one of them, ours included, still chose to go anyway. They chose to spend some of their limited, irreplaceable years building rockets, training astronauts, launching probes toward worlds most of us will never personally see. Maybe that's the actual answer buried underneath all the math and the mission profiles and the light-year conversions. How much of the universe could a human being explore in a lifetime isn't really a question about distance at all. It's a question about how a species chooses to spend its short, limited time once it fully understands, for the first time in its own history, just how small its reachable portion of existence really is. We could have looked up at the impossibly vast, permanently unreachable universe stretching in every direction and simply decided none of it mattered. We could have decided the distances were too great, the cost too high, the odds of ever truly leaving this solar system too slim to bother trying. Instead, we built telescopes capable of photographing light older than the Earth itself. We sent machines to touch comets, drill into Martian soil, and fly through the icy plumes erupting from a moon of Saturn. We put footprints on another world, and we're actively planning to put more there again, on the moon, and eventually on Mars. Within the lifetimes of people alive right now, watching this very moment unfold. That's not nothing. That's not even close to nothing. That's the real story of how much of the universe we could explore in a lifetime. Not a story about the limits of ambition. A story about the honest, unavoidable relationship between how big the universe is, how fast light travels, and how short, in cosmic terms, a single human life actually is. And within that short life, we can still touch worlds no one has ever stood on. We can still be the first eyes, in person rather than through a camera lens, to see canyons on Mars, oceans on Europa, rings up close around Saturn. That's not a small, reachable universe. That's an entire universe of firsts, waiting quietly, just a few years of travel time away, for whoever decides that 50 years is more than enough time to spend it well. Thank you for joining me tonight on this exploration of just how far a single human life could actually carry someone across the cosmos. If this changed the way you think about distance, about time, and about what exploration really means, please take a moment to like this video and subscribe to the channel. It helps this channel reach more curious minds, and it helps us keep making these deep dives into the universe and our place within it. And the next time you look up at the night sky, remember what you're really looking at. A universe almost entirely out of reach, stretching in every direction for tens of billions of light years, most of it forever beyond anything we could ever touch. But also a small, precious bubble around our own sun, close enough, reachable enough, for someone alive today to actually go there. 50 years is not very much time, but it's enough. Sleep well tonight, knowing that somewhere close by, in cosmic terms, there are still whole worlds waiting for the first footprint. Good night.